This video is brought to you by our amazing supporters over at Patreon. Hey everyone, it's Ben from Board to Bits, and today I'm going to show you how to create a special class or component that you can add to a planet object in a game to procedurally create some rings around that planet. It's a kind of a cool visual effect, can add some variety. If you have like a space scene, can certainly add some variety to that. Maybe even some gameplay involvement of those rings, but basically it's going to be able to kind of procedurally generate this mesh for us. We're going to have some controls that let us choose how high the resolution of the curve is, as well as its radius, where the ring starts, and how thick that ring is, and then we can apply a material to it to kind of give it that signature kind of Saturn ring type look. And basically the result of all this is that when we hit play at runtime, it will create this second planet ring object for us in the mesh that creates here. Also worth noting, I am going to be creating this so that we can see both the top and bottom of it. You may not need that in your game, and so if that's the case, there's going to be certain parts, and I'll try to point those out, that you may not actually need if you only need one side of the rings and want to save those triangles. Just a quick note, I am kind of assuming as I'm doing the coding in this particular video that you understand the basics of how a mesh works in terms of vertices, triangles, things like that. If you're not familiar, I encourage you to watch my series on creating custom meshes in Unity, but otherwise I'm not going to kind of dive quite as deep into why I'm setting up the mesh the way I am. So with that, we can get started. Okay, so before we start coding, I'm going to do a little bit of scene setup here and create some assets we're going to need. I've got this example folder here that was just for the intro stuff that I was doing, so don't worry about that. We're going to do everything from scratch from here. So first thing I'm going to do, I'm going to go up to Game Object. I'm going to create a 3D object sphere, and I'm going to rename this to Planet. And that's just going to be our kind of representative planet, not textured or anything, but it just kind of serves as the body that the rings will go around. I'm going to go over to our main camera, and I'm going to change the clear flags here from skybox to solid color. And I'm just going to change this to like a dark gray, just to give it a little bit more of a space feel. Lastly, I'm also going to move the camera. We're going to move the camera to a Z position of -2.5, so it's going to be a lot closer to the planet. And we're going to set its rotation on the X value to 25, so it's pointing down a little bit. Now it looks like here in mine at least, the planet is not at the origin, or it's not at 0, 0, 0. So I'm going to fix that quickly, and sure enough, I think my scene view must have been adjusted a little bit. So I'm going to just quickly right-click and reset that. Yours might have been already, but if it wasn't, just make sure that that's at 0, 0 and all. And then in our directional light, this is much more optional, but it gives a little bit better of the effect of the rings. If you adjust this a little bit, we're just going to change this here, the rotation, to 9 on the X, 81, and 25. And so this gives us this kind of more sidelong light that will really, like I say, kind of accentuate the effect of the ring once we create it. I'm going to quickly save our scene here. I'm just going to call this ring. And I do need to create a couple of assets as well. The first thing I need to do is I need to create a texture and then a material for the ring itself. You could just obviously have a plain solid colored ring, but I think it looks a little bit better and again kind of enhances it to have some texture there. So I'm going to import a new asset. And I'm going to import this ring texture here. I'll include a link to this file in the show notes, but you can also, it's really just a very simple file. It's only about 16 pixels to a side. And the one thing you're going to want to make sure that you check is that the filter mode here is changed from bilinear to point. It will work okay bilinear, but it's kind of, again, it has a little bit better of an effect with the point filter. You want your wrap mode to repeat, and you do want your alpha source to be the input texture alpha. So we'll apply that. With that in place, I can create a material, and I'm going to call this ring material. And this, I'm going to, in the albedo here in the main maps, add our ring texture. Now I have 2 here. That's because I actually have this texture in the example folder as well. but this looks like it's the one that's just in the asset, so that's fine. We'll use that. And you see that kind of appears there, but we're not seeing, there is actually a band of transparency in that, which we're not seeing because we need to change this from opaque to cutout, and you see that now cuts out that line. Lastly, I'm going to drop the smoothness down to 0. You can set it to whatever you'd like. I think it looks a little bit better if it's just kind of a flat appearance, and so we'll keep it like that. All right. With all those in place, now all we have to do is actually create the script that's going to actually produce this ring. So we'll go create C# script, and I'll call this planet ring. And again, this is going to be a mono behavior that we're going to be able to attach to the actual planet object, and then it will create the ring object at runtime. So I'm simply going to drag this onto our planet, and you'll see that it appears here as a new component of the planet. And with that, we can actually save our scene once more and jump into MonoDevelop to create this script. So in our script, we're going to want a few settings and references that we can use. So first I'm going to create some manual settings. And these are all going to be public variables. So the first one I'm actually going to put a range attribute onto. This is going to be a range from 3 to 360. And this is going to be a public integer called segments. And this is how many segments the ring will be made up of. Less segments is going to look more angular, more is going to look rounder. You probably would never actually need to go all the way up to 360, but I figure since it's a circle, 360 degrees feels like a reasonable number to cap it off at. Next, we're going to put in a public float called inner radius, and this is how far away from the center of the planet the rings actually start. You would technically want this always to be at least bigger than probably the surface of your planet. Although if you're looking for a particular look, it could, I suppose, intersect with the planet as well. But that's really all that this is going to set for us. And we're actually going to set that equal to about 0.7. So because our sphere, the basic sphere in Unity is half a unit radius, so 0.7 gives us a little breathing room. Likewise here in segments, I am actually going to set this equal to 3. If you don't, the range won't actually take effect at first, and this will just default to 0, and that can lead to some unwanted effects. So we'll set our segments equal to 3, inner radius to 0.7. We're going to do another public float called thickness. This is how thick or how wide the rings are. And this I'm going to just simply set to about 0.5. And finally, we're going to create a public material reference called ring mat, or ring material. That we obviously can't set in the script, but now if we jump back over to Unity, be sure to save your script. If you look at the planet and we look at the component now, we have these options. We have the segments, which is defaulting to 3 right now. We can even increase that maybe to something like 21. That's fine. Inner radius and thickness work as they are. And lastly, for our ring material here, I can drag in that material we just created. Save our scene, jump back over to our script. Now, the other thing, like I said, we're going to have are a few cached references. And these are basically so that we can easily access the parts of the ring since they're not technically on the same object as our planet. So I'm going to say cached references, and we will have a game object called ring, a mesh called ring mesh, a mesh filter, which is the component that holds the mesh, which I'll just call ring mf, and a mesh renderer, which we'll call ring mr. Now, none of these are public right now, so if we ever did want to access them from somewhere else, we would need to make either make these public or make some properties that can access them. We're not going to need the update function at all. We're going to do everything right from when we start our scene. And there's really 2 steps we're going to take here. First thing we're going to do is we're going to create the ring object, and then we'll actually build the ring mesh. So to create the ring object, we're going to take a few steps here. The first thing we're going to do is we're going to set our ring variable that we had equal to a new game object And we're simply we're gonna give this a name now, because if we go down here, we can see we can add a string for a name. And that will be the name of our planet, whatever we named it, plus ring. So that when it appears in our hierarchy, we can see it and go, oh, this is the ring associated specifically to that planet. Now, the other thing that's going to help with this is that we're now going to parent it to the planet. So we'll say ring.transform.parent equals the planet's transform. We're also going to make sure that everything, once we've created this, say we have a planet that is offset in the world somewhere and it's tilted and might even be scaled differently, we want to make sure all of those, the ring's scale and position and rotation are all kind of reset to 0 based on this planet. So I'm going to quickly say ring.transform.local_scale, and I want that to be equal to vector3.1. So it's going to be a scale of 1 on the x, y, and z. Likewise, local position will be vector3.0, so it's positioned at the exact same position as the planet. And ring.transform.local rotation will be equal to quaternion dot identity, which is basically the equivalent of saying vector3.0, but in quaternions. Lastly, we're going to set our cached references. So the ring mesh filter that we had is going to be equal to, and we're kind of going to do two things at once here. We're going to actually take our ring and add a component to it, but when you add the component, it actually returns that same component, which is how we're going to be able to add the mesh filter and assign it at the same time. So we'll add mesh filter to that, and then our ring mesh is going to be equal to the mesh filter's mesh. Likewise for the mesh renderer, same thing. We're going to say the mesh renderer equals, and then add a mesh renderer component, all in one line of code. And then finally, we want to make sure that our mesh renderer's material is set to that ring material that we assigned in the inspector. So that creates our ring object. If we, in fact, save this right now and go back to Unity, we can hit play and see that we get this little arrow, and we can see that planet ring gets created, and it has a mesh filter and it has a mesh renderer. Obviously, we haven't given it any triangles to render yet, but that is appearing now. So now we can actually build out the mesh of this ring. So the first thing we need to do is we need to create the arrays that are going to store our vertices, our triangles, and our UV coordinates. So first off, we'll do a vector3 array called vertices, which is going to be equal to a new vector3 array. And the size of this is going to be the number of segments we have plus 1. And the reason for that is that the very starting point of the ring, we actually need to double up and have another set of vertices at that point at the very end, because we don't necessarily want them to be the exact same UV coordinates. So that's why we're saying segments plus 1 is that last final edge. We're going to multiply that by 2 because we need both the inner radius and that outer final thickness. We need a vertice at the inner radius and then one at the outer radius. And then finally, we're going to multiply that by 2 again because we need vertices both for the top side of the ring and for the bottom side of the ring. And so that's why we are saying times 2 and then times 2 again. You could just say times 4, perfectly reasonable. I separated out that way just so I can kind of remind myself there's a reason that I'm doubling it twice. In addition to this, we need our triangles, which are going to be an integer array called triangles. And this is equal to a new integer array of segments. And this one is just segments, actually. It's not plus 1, because this is basically every single segment is its own quad in our mesh. And so it's really just segments times 6. And then we are going to multiply this by 2 again as well because we have top side and bottom side. And then we finally will have a vector 2 array called UV, which is actually the same amount of it's going to be the same amount of data points as the vertices because it's every vertex needs to have a UV coordinate to assign as well. And so for that, we're going to actually say the same exact amount. So we'll say segments plus 1, and then times 2 and times 2. The difference here being that it's an array of vector 2s and not of vector 3s. Lastly, I'm going to create kind of a helper variable here, and I'm going to call this an integer called halfway. And this is because, like I say, because we're doing both the top half and the bottom half, or I should say the top side and the bottom side of the rings, we're basically doubling the amount of vertices we need. And so that vertices 0 is going to be the first vertex of the top side, and then halfway through our huge array is going to be the first vertex of the bottom side. So the halfway integer is kind of just a handy offset on how to phrase that. So we'll say halfway equals segments plus 1 and then we'll multiply that by 2. Okay. With all those in place, we can now actually kind of loop through each segment of our ring and create quads for it. So we're going to say for int equals 0, int I equals 0, I is less than. Now normally when you do a for loop, you kind of have a number and you just go less than that number. We actually need to do segments plus 1 because again we're building out that final extra edge of vertices as well, and so we do need to make sure that we actually do one more loop at I equals segments. So we'll say I equals segments plus 1 here, and then I plus plus. And now the first thing we're going to do now is we need to determine where we are along the process of going, orbiting around the planet, if you will. So when we start, we're at kind of a 0 point. We're going to work our way around the circle, around all of the degrees, and at the end we'll be we'll have done one full loop of the circle. And so to represent this, we're going to create a float called progress, and this is going to be equal to the float of I divided by the float of segments. And so what this means is that when we first start, I is 0, that means that 0 divided by the number of segments is still 0. When we get to the very last loop, it's going to be equal to segments, so that's going to be segments divided by segments. That means we'll be at 1. So we're going to basically progressing through these loops from 0 to 1. And that gives us a nice kind of normalized representation of our progress around the circle. Next thing we're going to do is we're going to find the angle that we currently are on the circle by using float angle equals mathf degrees to radians, which is just kind of a constant number, times that progress we've made, times 360. So this is basically how much progress we've made in degrees, and then we're going to convert that to radians with this number. Now using that, we can actually get kind of the x and z positions of each vertex around the circle by using the sine and cosine of that angle. So we'll say float x equals mathf.sine of that angle we figured out, and float z equals the mathf.cosine of the angle. The reason we're doing x and z is that y kind of represents the axis of the north to south pole, and we're going to kind of assume that these rings go around the equator. With that information now, we can actually start creating all of our vertices. So we're going to say vertices I times 2 equals vertices I times 2 plus halfway. And so that's getting us, like I said before, that's that kind of freebie offset that we created so that we're getting both the top side and the bottom side of the rings all at once. And we're going to set both of those equal to a new vector 3, which is x, 0, and z. So the x and z that we calculated, and then y is just always going to be 0. And we're going to multiply all that times the inner radius plus the thickness. So this is actually going to get us the outside vertices of the ring. And then on the inside, we're going to do the same idea. So we're going to do I times 2 plus 1. Because we're basically just, as you can see here, I times 2, this is going to go up basically even numbers. So this gets us the odd numbers in between. Likewise, we'll do vertices I times 2 plus 1 plus that halfway offset. So same idea, just on the bottom side. And this is going to be pretty much the same thing. We just don't need that thickness anymore. We only are interested in the inner radius. So I'm simply going to copy this, delete that extra parenthesis we don't need, and that gives us the same angle, but just to the inner radius and not to the full thickness of the ring. So that gives us basically the 2 points at the particular angle that we're at on the inside and the outside of the ring. We can also find our UVs right now, and basically how our UV points are going to work is basically that the points are going to go along the width of that texture that we created or imported, and one's going to be at the top and one's going to be at the bottom. So we're going to say UV I times 2 is equal to UV I times 2 plus halfway is equal to a new vector 2, which is simply going to be that progress we're making along the circle, and the first one will be 0f. Helps if I spell progress correctly. And so this means that we're moving horizontally as far as we've progressed, but then this one will always be at the bottom of the texture. And then for the inner edge of the ring, we'll have UV I times 2 plus 1 again. This is really just reflecting those vertices, equals UV I times 2 plus 1 plus the halfway offset. And this is going to be equal to basically the same thing again, but now instead of the bottom of the texture, we're going to go all the way to the top. You can actually have some interesting effects if you change these, say, and only use a certain segment of your texture. It's a great way actually to get some variability out of one texture if you have multiple planets with multiple rings. Lastly, now we need to actually determine what the triangles are that make up these quads. And we only need to do this actually for every single segment except for the last loop, because that very last loop, remember, is we're simply creating the vertices for that last edge, but it doesn't have its own quads associated with it. It simply finishes the previous quads. So we're going to do a quick check and say if I does not equal segments, just to say if we're not on the very final loop, then we actually do go ahead and create these triangles. And this is going to be, I'm going to kind of do this quickly here because this is the section, like I say, that you need to know how quads work. This looks pretty arbitrary, but if you understand how quads work in creating meshes, then this is why you do it this way. So I'm going to start, and I'll probably just kind of speed through this once I get through a couple lines of it, but we're going to say triangles I times 12 equals I times 2. The reason it's 12 is that we're actually creating 4 sets of triangles, the 2 quads for the top, 2 quads for the bottom, so every single loop is going to be an iteration of 12 triangle vertices. And then the I times 2 is just how it's pulling from the vertices array. And then we'll have triangles I times 12 plus 1 equals I times 12 plus 4. This all equals I plus 1 times 2. Copy all this. This becomes 2 and 3. And this becomes I times 2 plus 1. And then finally, times 2 plus 5 equals I plus 1 times 2 plus 1. Like I say, this looks like a lot of very arbitrary math, but basically what we're doing here is we're getting the two vertices of the edge we created along with the next two to create these sets of two triangles. Now this is all just for the top. We also need to get those vertices that are involved on the bottom side, and that's what the next 6 of the 12 are going to be. So I'm actually just going to copy this and add in. So then the next one would be number 6, and then we work with 7 and 10, 8 and 9, and finally number 11. And these here are times 2 plus halfway. This one down here is plus halfway. And because we're on the flip side, we actually need to reverse the orders of these triangles. So we're going to switch these two around and add halfway here as well. So I apologize again, seems kind of arbitrary, but like I say, if you're, I'm going to kind of be asking you to just kind of follow that along because I say so at the moment. If you'd like to know more about it, I really encourage you to watch the mesh series I did. Once we've done all this, we've actually created all of the mesh information. We just now need to give it to the actual ring mesh. So what we'll do is we'll jump out of our for loop, we'll close off this for loop, and then we can assign all of these vertices and triangles and UVs to the ring mesh itself. So we'll say ring mesh dot vertices equals the vertices array we've just created. Ring mesh dot triangles equals the triangles array. Ring mesh dot UV equals the UV array. And then finally we're going to say ring mesh dot recalculate normals. And what this does for us is this makes sure that based on how we've created our quads, our vertices all kind of point so that those quads get lit correctly. And that's the big reason that we created both a whole set of vertices for the top half and for the bottom side of the rings, because we want to make sure that the top ones are pointing upward, the bottom ones are pointing downward. Otherwise, recalculate normals wouldn't really know what to do. In fact, you would never be able to get the proper lighting for the rings because your vertices can only point and can only face in one direction. So with all that, we can jump back over to Unity, take a look at our planet here. Everything looks like it's compiled. And so now we'll hit play and we should see a pretty round, this is a pretty good number for some fairly round rings here. So let's hit play and there they appear. You'll notice we get this nice shading from the planet. That's because of the light, how we changed the angle of the light. You can see some of the lines there, but it's still pretty round, which is a pretty good shape. And then if I take this here and I go under, you can see that down there it's dark because it's not getting hit directly by the light. So that's why those extra vertices help out and give it a little bit of a better look. But yeah, this gives you this nice band of transparency here. Gives you a nice, pretty realistic looking planet rings. You can even go so far if you were to rotate the planet. You see that the rings always what's nice about being, kind of centered on the planet is that this will now reflect whatever angle, scaling, and position changes the planet does. So with that, that really wraps up this video at this point. Feel free to take this even further. I'm probably going to do one more video where you can see, kind of make these adjustments and see them in real time using a special event call. But beyond that, hopefully this gets you started and is a cool effect for your games and helps you if you're working on some kind of game that needs a planet with a ring. So thanks so much for watching, and I'll see you next time.